better performance of the gallium arsenide technology. The transition from vacuum tubes to silicon, to the silicon integrated circuit, was a drastic step. I mean, it was a completely new technology. And I think that the problem is in going from silicon to gallium arsenide, you're going from one semiconductor technology to another, and there are still many discussions. Is this the right material? Should it be something like silicon carbide? Can we do better with going to submicron silicon? And I think that it does have some desirable attributes. It has greater radiation hardness than silicon, but it's that in itself I don't think is, it's not that hard. But going on to the next slide, the problem is it's a compound, not an element, and it's poor thermally, it's brittle, and so forth, so that you've got to really want to use it in order to go forward into it. But I think that the real thing, it does offer the potential of the higher speeds and power at higher frequencies that we cannot get with the silicon technology, and it is going to be a key technology for the active aperture radars and for the communication satellites and direct broadcast satellites of the next century. And I think in the last slide, this is a cartoon I got out of the Post back in January, and the caption says it destroys everything within a 10-mile radius, but it has a range of only 9 miles. Well, I think the synergism between military and commercial in the gallium arsenide area is going to allow us to change that 9 miles to 11 miles. Thank you.
Thank you, Ward. Well, we have a few minutes left. If you have any systems questions, in the injection of technology into systems, you have the right man on the roster. Any questions from the floor? Yes, sir.
What is the relationship between the VISIC program and the gallium arsenide developments?
None.
Thank you.
There needs to be a VISIC-like gallium arsenide thrust. In other words, in gallium arsenide, we need something like a $500 million type program with multi-contractors and so forth if it's really going to get here even by the next century, really. That is for the wide scope of applications that there are in military. Yes, sir.
Most of the processing is now digital. And I think you said that the gallium arsenide is more appropriate for analog processing. Does that pose a problem?
It's not. Well, first of all, you can make digital optical microwave structures in gallium arsenide that can be used as digital computers and so forth. And using the optical fibers and so forth for transferring the energy around. I think that the key thing on gallium arsenide, it is a high efficiency amplifier, and it is faster because of its higher mobility, and but it is not as convenient to a substrate material to make the various other circuit elements on as is silicon. It doesn't have a native oxide and so forth and so on. But I think that Harvey would probably like to address this topic since he's a specialist in the area.
I'll just say two sentences. There is no question that gallium arsenide is superior above, say, 5 to 8 gigahertz for linear microwave amplification. But right now there's still a question as to whether one should go to gallium arsenide for any digital system. The trade-offs between complexity, fabrication yield, and the increased speed that you get are not clear. So a lot of the talk that Warren addressed was on linear devices where there's an absolute certainty of a niche up as high as 94 gigahertz.
Well, am I correct that the huge majority of processing is digital? So it seems like the application of gallium arsenide might be minimal, considering the fact that all the processing I know of now is digital?
Well, I think that the fundamental thing is in most all of your systems, let's take an antenna system, you're interested in moving the processing as close to the radiating element as possible. Now, this leads to active aperture type radar systems or EW systems, or in some cases communications systems, although in most cases the communication system does not require agile beam operation. All right, to do that you need amplification, linear amplification, power amplification at the radiating element of the antenna, and that requires gallium arsenide. And one of the things that you were doing there as part of it, you may be doing digital beamforming, and you may translate the frequency from X band or wherever the system might be operating down to some frequency at which a silicon device could provide the A to D converter and so forth. And I think that the key thing is, if you are looking for 5 gigahertz clock rates or something like that, gallium arsenide is the only material that you can use. But I think that it is a material that whose high speed does have a role in, I think, ultimately in the digital world as well as in the analog world.
I have just had a request.
Could I ask one more
Go ahead.
follow-up question on that? I'm still a little stuck on it. Are you implying that as far as digital circuitry is concerned, that it will be primarily silicon for the foreseeable future?
No.
Can I address that? I hope this will throw some light. Just a brief statement. Gallium arsenide has much higher mobility than silicon. The electrons move much faster. So for a given size, you can get higher speed circuits. Insofar as speed is the criterion, there's 2 ways of going. One is to have higher mobility material, electrons move faster, or closer spacing, which is the Visick thrust. So you've got 2 competing technologies. One uses a material in which the electrons move faster. One uses the old mainstream material, but gets closer spacings. That's the competition, as far as digital circuits are concerned. Linear circuits, gallium arsenide has it, no question.
I want to try. Silicon gallium arsenide. For blinding speed, the absolute speed that you need, gallium arsenide looks wonderful if you're not worried about the power dissipation, or, in other words, complexity. But a lot of digital people are sort of worried about speed-power product. That's the thing they like to talk about, both in Visick and gallium arsenide. That's where things are a little questionable. But if you want blinding speed at the front end of an antenna, as Warren said, gallium arsenide looks very promising. If you want all the complexity associated with a microprocessor at the front end, a little bit of a question, because there you need both packing density and speed, and the trade-offs thereof. Are there any other questions for yes, ma'am?
Defense funding is now being funneled toward gallium arsenide, and who are the major players for this development?
Oh, Leo, do you want to address that?
I don't know how much. Offhand, it's a lot less than silicon, that's for sure. And I think it's more in the early areas, the research and early development areas, rather than further on. In terms of dollars, gosh,
1/10.
fun? No, it's more than that. It's in a few million, but I don't know how much. It's nowhere near the hundreds of millions that goes into silicon.
Oh, I would say probably tens of millions a year.
Yeah, maybe so.
I think in the areas of digital applications, say a gallium arsenide RAM is being developed by a couple of major companies. Can you just summarize where the developments in gallium arsenide technology are being directed specifically to the digital? Say the RAM chip, what else?
Harvey will address that.
Well, there are a lot of government programs in ultra-high-speed A to D conversion. There are programs being let that ask the question, Can you do real-time conversion at 3, 4, 5-bit accuracy at, say, 2, 3 gigahertz? Some companies are even targeting getting up to X-band and doing baseband A to D conversion at the multi-bit level. So that's another extremely important area. The all-digital antenna is the thrust of many EW and radar systems. I have one more question for you. Don't leave. And then you can all take off.
Please address it to the microphone.
Yes,
Mark.
sir. This is a question from the floor. Warren says that there's going to be this wonderful synergy between the commercial sector and the industrial sector. I believe that. Military sector. But what I'm a little apprehensive about is the role of our friends from the Far East. The Japanese are wonderful in commercial applications. And if we're going to have a synergy with the commercial sector, and the commercial sector has a very strong Far East component, what does that say about the synergy? Will that synergy work as well as we hope it will in the future?
Well, I think the fundamental thing, certainly in the near term, we're going to have to use technology from wherever we can get it. But I think that we have got to have an onshore base of that technology so that we are not at the mercy of somewhere beyond our borders. I think you would agree with that, wouldn't you, Leo? So, I mean, is that a satisfactory answer, Harvey?
Harvey, can I make a comment about that? Brief. I think the university will play the key role in this context. We don't have in this country a MITI. I think the universities are the MITI of this country for the industrial government interplay. And it's happening already.
Makes a lot of sense. Well, we'd like to thank you very much for your time.